Welcome back to Chapter 3. In this section, Section 5, we're going to be looking a bit at solving exponential and logarithmic functions, as well as a little bit of modeling to go along with it. Our learning targets for today: to solve exponential equations algebraically, to solve logarithmic equations algebraically, to find the domains and graph logarithmic functions, the domains of and graph, to solve exponential and logarithmic equations using more than one method. We will see some more methods, and then graphing is always a method. And then determine orders of magnitude. So, our first step is solving exponential equations. Now, when we're solving exponential equations, and logarithmic equations for that matter, there are a few different ways that we can do it. The first is to look at one-to-one properties. What that says is that if you have a number to a power which equals another number to a power, that means or equals the same number to a power, it means the powers are equal. So something like 3 to the 2x equals 3 to the x minus 7. We have 3 to a power equals 3 to a power. That means that 2x must equal x minus 7. And we can solve. We can subtract x. 2x minus x, just x, equals negative 7. There we go, because the two powers were the same. Now, that won't generally happen quite like that. And we might get something more like this. 16 to the 2x equals 64 to the x minus 5. Well, here, they're not both the same base, but we can turn those into the same base. 16 is 4 squared, so that's 4 squared to the 2x equals 64 is 4 cubed to the x minus 5. We have powers of powers, so we can multiply those. So this will be 4 to the 4x, and this will be 4 to the 3x minus 15. Now, it looks kind of like that first problem. The bases are the same. That means that 4x has to equal 3x minus 15. We can subtract the 3x over to get x equals negative 15. So we can force them into that situation. Sometimes we'll get something like this, and it's not in that situation at all, or at least it looks like it. Well, when we're solving anything like this, we want to get the something to the power equals a number. So here we could divide both sides by 20. So we have 1/2 to the x over 3 is going to equal 5 over 20, which reduces to 1/4. From here, there are a couple different things we could do. We could write them using the same base. So we get 1/2 to the x over 3 equals 1/4 is 1/2 squared, which means x over 3 has to equal 2, which means x equals 6. We could have also taken the log of both sides. Take the log of 1/2 to the x over 3 equals log of 1/4. The x over 3 can move out to the front, so we get x over 3 times log of 1/2 equals log of 1/4. Divide the log of 1/2, because log of 1/4 and log of 1/2 are just numbers. They are not pleasant numbers, but they are just numbers. So we can divide. So we'll have x over 3 equals log of 1/4 over log of 1/2. So log of 1/4 is an unpleasant number. Log of 1/2 is an unpleasant number. What happens when you divide two unpleasant numbers? Well, really anything. You might get an unpleasant number, or in this case, you get 2. So we get x over 3 equals 2 again, which was the same thing that we got right up there. And so x would equal 6. So there are different ways of solving these. Sometimes, for instance, if we have 3 to the 2x equals 7, we're not going to write those using the same base because they don't have anything in common. So now we have to take the log of both sides. Log of 3 to the 2x equals log 7. The 2x can come out in front. And then we can divide by that log 3 to get 2x equals log 7 over log 3. Now log 7 is an unpleasant number. Log 3 is an unpleasant number. This time when we divide them, we're probably still going to end up with an unpleasant number. So when you're doing this, use a calculator. And in addition to using a calculator, like I would go log 7, enter, you get about like 0.845, blah, blah, blah. And then the next button I would push, divide by, then log 3 to get 1.77124. So 2x is going to be 1.77124. Now, I write just a few decimals there. I'm using whatever's in my calculator though. Like I don't need to write out every single digit, but I am not going to clear it and retype it. I have this, next step we have to divide by 2. So I have that in my calculator. I'm going to hit divide by 2. It's going to be the answer divided by 2 is 0.8856. Make sure that you can write down fewer things, but make sure that in your calculations you don't round until that very last step. So that's a way where we had to use logs to do this. We have other things that taking the log of both sides here won't actually work because we need something to a power equals in order to take a log of both sides. What we could do here, the first step, I would multiply by 2 just so we get rid of that fraction. So we have e to the x minus e to the negative x equals 10. Well, now what can we do? Well, we can multiply everything by, say, e to the x. Why would we multiply everything by e to the x? Because this is a fraction. This is 1 over e to the x. So we still have that fraction there. Now when we multiply everything by e to the x, we'll have e to the 2x minus 1 equals 10 e to the x, which doesn't look like it's much easier to deal with, but I'm going to move this 10 e to the x over, going to subtract it, and I'm going to rewrite this ever so slightly. Instead of e to the 2x, I'm going to write that's e to the x squared. Then we'll have minus 10 e to the x minus 1 equals 0. This should look a lot like a quadratic. We have something squared minus something times the thing minus 1 equals 0. We could factor this. Well, we can't factor this one because it's not going to be factorable, but we can use the quadratic formula. It is possible we could factor it. When we use a quadratic formula, instead of x equals something, we're going to have e to the x equals something. Our a is 1, our b is negative 10, our c is negative 1 still. So we'll have negative b, so it'll be 10 plus or minus a square root of b squared minus 4 times a, which is 1, times c, which is negative 1, so that'll be plus 4, all over 2a. So e to the x will be 10 plus or minus the square root of 104 all over 2. 104 is, we could divide by 4. So that would be 10 plus or minus 2 root 26 over 2, which we can simplify that. We get 5 plus or minus root 26. Root 26 is going to be 5 point something, right? 5 point something small. If we subtracted 5 minus root 26, we're going to get a negative number. E to the x has to be positive. Exponential functions are positive. So 5 minus root 26 is not going to be an answer here. But we could have e to the x equals 5 plus root 26, which is a value. It'll be 10 point something. And then what we'll do to get rid of the e, we have to take a log of both sides. In this case, since we have e, let's take the natural log of both sides, which will give us x equals the natural log of 5 plus root 26, so 5 plus that 10 something. And when we do that, we get that it's about 2.31. Again, that part is just a type it into the calculator type of a part of that question. But we get that. And that one, like, we had to do a lot of work before we could just take the log of both sides. Solving logarithmic equations, it's kind of the same. If we have log of a base equals the log of a base, like they're the same, then the insides have to be equal, just like we did with the exponential functions. But we'll have other ones where we have to use other methods. So here, we could use a one-to-one method where we have log base 10 of x squared equals 2. Well, 2 could be written as log base 10 of 100. And so x squared has to equal 100. That's a way to do it, but that's not going to be as useful because if it didn't equal 2, if it equaled 2.1, we're not going to be able to figure that out easily. The other way of doing this is use an exponent. So we have log base 10. So we're going to take both sides to the 10th power to get x squared equals 100. Then we can square root both sides to get x equals plus or minus 10. Now, there is another method which you have to be careful about. We have log of x squared equals 2. Using this property, the power property, to go 2 times log x equals 2. We can divide to get log x equals 1, and then go 10 to the power and 10 to the power to get x equals 10. We lost one of our roots. We lost that negative 10. And so which one is right? Well, if we graphed this one, we would see that it does in fact have two solutions there because the log, the argument of a log has to be positive. Well, x squared is always positive, so we do get that mirror reflection there. Whereas when we were down to log of x, that's only positive on that positive side. So when we did it that second method, we lost this whole side of the graph. So it's important to be checking your answers. Make sure it makes sense. Make sure that that's the only answer that you have. This second method isn't necessarily a bad method, especially if we know that the whatever we're looking for has to be a positive value, which in application problems is generally the case, but we do want to make sure that we don't accidentally forget about a solution. Another one, a little bit bigger one. For this one, we want, if we can get a log of something equals a log of something, then we can use that that property we saw on that last page, where the two somethings have to be equal. So we can use our log properties. Log of 3x minus 2 plus log of x minus 1. So when we're adding, that means we could multiply these. That's ln of 3x minus 2 times x minus 1 equals, and then this 2 can come up top, natural log of x squared So now we have a natural log of something equals natural log of something. That means that 3x minus 2 times x minus 1 has to equal x squared. We can multiply this stuff out. So we have 3x squared minus 3x minus 2x minus 5x plus 2 equals x squared. Subtract that x squared over. So we get 2x squared minus 5x plus 2 equals 0. Now we can factor. So we'll have a 2x and an x. So 2 will be a 1 and a 2. We can multiply one of those by 2. So we'll have a negative 4x minus x is negative 5x. Negative 1 times negative 2 is 2. So that works out. So here we have x equals 1/2 and 2. Now we have to be careful here because we need to put these into each of the original equations. So if we put the 1/2 in, we get natural log of 3/2 minus 2 plus natural log of 1/2 minus 1 equals 2 times natural log of 1/2. 3/2 minus 2 is negative 1/2. 1/2 minus 1 is negative 1/2. We cannot have a negative inside of a log. So this one does not work. That's a superfluous solution. And if we graphed it, we would see that we don't have this other side of the graph in this case. So that doesn't work. We could plug in 2. Natural log of 3 times 2 is 6 minus 2 plus natural log of 2 minus 1 equals 2 times natural log of 2. So natural log of 6 minus 2, that's natural log 4 plus natural log 1 equals 2 times natural log of 2, which we could bring that up to get natural log of 4. This works out because natural log of 1 is equal to 0. So we get natural log of 4 equals natural log of 2 squared. So that works out. So the 1/2 doesn't work, but x does equal 2. And again, graph it. Use a graph to check those answers. Make sure they make sense. Make sure you're not missing one. Make sure that they both work. Orders of magnitude. So orders of magnitude is basically just how many times you have to move the decimal point. How many times would you multiply by 10 to get from one number to the next? A meter is 2 orders of magnitude bigger than a centimeter because you multiply a centimeter by 100, that moves the decimal point over 2 and you get meters. It doesn't have to be exact necessarily, but it gives that general range. And we use orders of magnitude because we have a lot of scales that are logarithmic and that measures orders of magnitude. And on a logarithmic scale, a 2 is 100 times bigger than a 1. A 3, or 10 times bigger than a 1. A 3 is 10 times bigger than a 2. A 4 is 10 times bigger than a 3. So a 4 is 100 times bigger than a 2. And so that's where the orders of magnitude come in. We have a number of different logarithmic scales. The luminosity, so the brightness of light, is a logarithmic scale. That's used for stars as well as light bulbs. Decibels is a logarithmic scale. The Richter scale is a logarithmic scale that measures the strength of earthquakes. We'll also see the pH level is a logarithmic scale. So the Richter scale, we have the equation R, that's the value we are told, like it's a 7.2, that's the R, is the log of A over T plus B. A is the amplitude of the little thing, like you see the, like, the little seismic graphs. A is the amplitude of that, of the vertical ground motion. T is the period, so how far spread out are they? And B accounts for the weakness and the seismic activity, or the weakening of the distance from the epicenter. The real number we look at here is going to be A. That's the one that we're going to use. And so we can find that. We'd have to know all three variables, or 3 out of the 4 variables, to solve for the other one. However, we can measure how many times more severe was the 2001 earthquake in Gujarat, India, which was a 7.9, than the 1999 earthquake in Athens, Greece, which was a 5.9. So we can set these up. We have a 7.9 is going to be the log of a 1 over t plus b, and a 5.9 is going to be the log of a 2 over t plus b. We're going to assume that the t and the b were the same in this case, which is a general assumption to make. Now, if we subtract these two things, 7.9 minus 5.9 equals log of a 1 over t plus b minus log of a 2 over t plus b. We're going to get 2 equals, so we have the log minus the log. That's going to divide, right? When we subtract, that means we divide. So we have log a 1 over t divided by a 2 over t. Then we have b minus b, that goes away. And then we have this division here. When we divide, we can flip and multiply. So we get 2 equals log of a1 over a2. So that's why we would subtract here. It's because that's those other things will go away. Now we could solve this. So we can go 10 to the power, 10 to the power. Come up here. So we get 100 equals a1 over a2. And so what that means is that the earthquake was 100 times as severe in India than in Greece. Because that's what it was asking, how many times more severe. So 100 times more severe. And so that's how we can use the Richter scale. I should not have moved it all the way over there. I'm going to rewrite it down here because I have another one coming up over there. So we're going here. So 100 equals a1 over a2. So it's 100 times more severe. That was bad because where's my next one? Oh, there we go. pH. pH is another thing that we use logarithmic models for. And the pH equation is just, it's equal to the negative log of H plus, and it's like in the square brackets, which is kind of a weird thing. That's a chemistry deal. It's the concentration of hydrogen ions in something. So it's negative log the concentration of hydrogen ions. And that negative in there is because when we take the concentration of hydrogen ions, which is going to be a very small number, like 0.00000 something, we're going to get a negative number. So that negative in the equation makes it a positive number. So what could we do? We have, some vinegar has a pH of 2.4, and a box of baking soda has a pH of 8.4. So we could find the hydrogen ion concentrations of both. We can figure out how many times greater the hydrogen ion concentration is in vinegar than in baking soda, and by how many orders of magnitude is the concentration differing. So, first step, what is their hydrogen ion concentration? We have vinegar first has a pH of 2.4, so we get 2.4 equals negative log of H plus, and that whole thing's just going to be a number. We're going to move the negative over, so negative 2.4 equals the log of H plus. Then we can go 10 to the power, 10 to the power, to get 10 to the negative 2.4 is going to be about 0.398 times 10 to the negative 3. Moles per liter. And you might be wondering, like, wait, why would there be burrowing rodents in this problem? A mole is it's a unit that we use in chemistry a lot. It's Avogadro's number. Right now, it's just part of a unit. It's a really large number. So we have that many moles per liter in vinegar. And then in the baking soda, that's going to have 8.4 equals the negative log of the hydrogen ion concentration. So we can make that negative 8.4. 8.4 equals the log of the hydrogen ion concentration. Then we can go 10 to the power, 10 to the power. And so in this case, we're going to get, it's about 3.98 times 10 to the negative 9, or 0.398 times 10 to the negative 9 moles per liter. And so that was A. That was what is their hydrogen ion concentration. Now, how many times bigger is one than the other? So that we can divide these two numbers. We can divide the vinegar divided by the baking soda. So we could use these 0.398 numbers, or we could also go, this is A, B, we could use the 10 to the negative 2.4, because that's what that is. 10 to the negative 2.4 over 10 to the negative 8.4. When we are dividing, that means we subtract. Negative 2.4 minus negative 8.4 is like plus 8.4, which is 10 to the 6th. So it is 10 to the 6th times bigger, or 10 to the 6th times greater, the hydrogen ion concentration 10 to the 6th times greater in the vinegar than in the baking soda. And so then it's asking how many orders of magnitude greater is it? And that, we just look for that exponent there. So it is 6 orders of magnitude greater than the baking soda. So that's that. Newton's law of cooling is another big application. Newton's law of cooling has a formula that goes with that, is the law. And so we have two different T's. We have capital T and lowercase t, because it's not confusing enough, so we needed to make it a little bit more confusing. The capital T is temperature. The lowercase t is time. So this would be the temperature at a certain time. Tm, This is the room temperature, the surrounding temperature. T naught is the initial temperature, and then K is a constant. So, using Newton's law of cooling, so what happens here is when I set my coffee cup down on my desk, it starts cooling down because it's hotter than the room. And it's going to cool down. It's not going to cool down indefinitely. It's not going to cool and then start freezing. It's going to cool down to about 55 degrees Fahrenheit because that's the temperature of the surrounding room. It will approach the surrounding temperature. Now, notice as the time goes to infinity, this part goes to 0 and it becomes room temperature. My coffee cup sitting on my desk is not going to change the temperature of the room, however. There's just not enough heat in the cup to be able to affect the temperature of the room. Now, yes, in extreme circumstances, that could change, in which case you probably would not be using this particular equation. But for normal situations, this is how it goes. So, what could we do? We have a hard-boiled egg at temperature 96 degrees Celsius is placed. So this is T naught, is placed into 16 degrees water to cool. That's Tm. And then 4 minutes later, the temperature is 45 degrees. So that's going to be a TT, which will allow us to find that K value. So we're going to set up a couple different equations here. The first one, we're going to use this extra information. 4 minutes later, it's 45 degrees Celsius. So we can go with it's 45 degrees Celsius equals the room temperature, which is 16, plus the difference, 96, minus 16. Notice that I called it the difference. That's the difference in temperatures, because it's going to cool differently if it's put into 16-degree water as if it was put into 86-degree water. That difference, the bigger the difference, the faster it cools. E to the negative k, and then t in this case was 4. So we have one variable here, it's just that negative k. We can start solving this. We can subtract the 16 over. 45 minus 16 is 29, equals 96 minus 16 is 80. There's an 80-degree difference. E to the negative 4k. Next step, we have to get the e by itself. Divide by 80. So we get 29 divided by 80, which is a number. It's not a particularly nice number, but it is a number. That's okay. We can leave it as the fraction. So we have 29 over 80 equals e to the negative 4k. Now to get that variable out of the exponent, we're going to take the natural log of both sides, which will give us negative 4k equals the natural log of 29 over 80, which again is just a number, not a pleasant number, but just a number. And now we can divide by negative 4. And just like before, don't be rounding. Like I would actually get to here, and then I would just put this into my calculator. And at that point, we get k equals about 2.53. I'm sorry, 0.253. So k equals 0.253. Now we can use that. That's a constant. That's going to go back into the equation. We can use that to figure out when the temperature of the egg will be 20 degrees. There are really two questions that it could ask at this point. It could ask, when will the temperature be something? And it could ask, what is the temperature at a certain time? If it's what is the temperature at a certain time, you plug that time in for t, and you just simplify the equation. That's definitely the easier of the two. So we're doing determine when it will be 20 degrees. So the new temperature is going to be 20 equals the surrounding temperature is still 16, plus we still have 96 minus 16, e to the negative k. K is that 2.253 number, and I wouldn't round that either. That's going to be, it's in your calculator. You can copy and paste that. You can actually save that to a value and like a variable. Then you can plug that in. You can go up to previous lines. There's all sorts of things you can do. But exponential functions, those exponents are so they're so sensitive. Like a little change will cause it to go very wrong. So I'd use as many decimals as possible. 0.253 to the t. And then this, we're going to solve it exactly the same way. Subtract the 16 to get 4 equals 80 times e to the negative k. I'm going to write the 0.253 t, divide by 80, and then we'll take the natural log. So we'll get natural log of 4 over 80 will equal the natural log of e to the power, which will be the negative 0.253t. We can divide by k. So you have k in your calculator. That should just be that last line. You have natural log of 4 over 80 divided by, go up to that last line, plug that in. So we get t equals about 11.81 minutes. So after 11.81 minutes, that egg is going to be 20 degrees Celsius. And so that's Newton's law of cooling. It actually works for heating as well. Like if you have an ice cube sitting on the table, like it's losing the temperature, works basically the same, except you have to subtract the other way. The other thing with Newton's law of cooling is if we took that Tm and we subtracted it over to be here, this now becomes just an exponential equation. And so we can make a model, we could do regression if we have data. Because remember, the regression gives us y equals a times b to the t. This is a times b to the t. The surrounding temperature is a constant. So if you know the difference, you can find the temperature at any given point. So in order to do like regression, to do a model, we need to look at the difference between those two temperatures, and then we can find what we're actually doing. And speaking of models, we can use logarithmic re-expression. When we don't have a linear model, we can make the data linear by using logs. Why would we want to do that? It's easier to see a linear model, and it's also we can do more with a linear model. Is this a huge topic? No, not even in statistics. Like it's a chapter, but one that's not really covered all that much. But we do have a few different types of models. We have linear, we have a logarithmic regression, we have exponential regression, and we have power regression. So we have a few types of models to work with. Now, if it's linear, then the scatter plot is going to be linear. If it's logarithmic, and we get this curve here, we can take, if we take the natural log of all the x values and graph them with the y values, it should be linear, which means that y equals m times natural log x plus b, and that verifies that yes, it is actually a logarithmic equation. So if you can take the log of the x values and it turns out linear, it's logarithmic. If you take the log of the y values and it turns out linear, it's going to be exponential. So exponential equations, we take the log of the y's, and they'll be linear. So instead of y equals mx plus b, it would be natural log y equals mx plus b. And then if you take the logs of both, you can actually get a power function, which is y equals a times x to a power. So like y equals x squared is a power function, but so is y equals x to the 7/3. And so logs of both x and y give you a power function when those become linear. And so it just helps to verify what it is. In statistics, we actually make them linear. We find the linear regression, then we retransform them back into the other one. You guys right now are just using it to check the fit of the model and the shape, especially exponential and power, because they look very similar to each other. Although when the power is like to the 1/2 power, you get square roots. Those guys look similar too. And so by doing this re-expression, you can help to weed those out. So with that, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.